All right, so welcome to the first video of quite a distinguishable biophysics course playlist. And being that this is the first video, we're going to kickstart with the bare essentials. So we're going to talk a little bit about waves. What are the differences between transverse and longitudinal waves, constructive and destructive interferences. We're going to talk a little bit about the electromagnetic radiation spectrum, just a little bit, and what does it contain? So this is what we're going to cover in this video. So let's get started. I do not use Wikipedia often, but I do find their definitions quite easy to take in. So this is from Wikipedia. A wave is a disturbance or an oscillation that travels through space and time. And basically, when we're thinking about waves, I do like to use intuition. So if I'm holding a rope, here. This is my rope, and I jiggle it up and down. I jiggle it up and down. What am I really going to observe here? This is a pretty deformed hand, but stay with me. What I'm going to observe is some sort of oscillation. This is the oscillation that I'm talking about. And little by little, we will see this oscillation traveling down the rope until it gets to the very end. And when you think about it, this oscillation, and hopefully this makes a little bit of sense, this oscillation is the one that is actually traveling the length of the rope. It's actually traveling the length of the rope. And what you need to bear in mind is that it isn't that particles of rope are being transported from one side to the other. It's not that particles that are here are now moved and they're now here. No, the particles are not moved, they're just oscillating. The disturbance itself is moving. And this is really what's important to understand. And if you want another example, and we can make it a little bit more intuitive maybe, if this is my ocean and I'm somehow creating a wave because I'm so powerful and I'm standing here and somehow I can wave my arms around and I can make a wave occur, then this wave is simply going to move across the water. It's simply going to move across the water. And it's not that water particles from this side are going to move to that side. No, it is that the disturbance, the wave itself across the water, is going to be the one that's moving. So the disturbance is moving. And what's quite important to understand is that in these two cases, the disturbance that is propagating here, either the wave or this little jiggle on the rope, they both have a medium. And the medium in this case is the rope. And when I say medium is, what is it propagating through? The wave is propagating through the ocean. So the ocean is the medium here. The ocean is the medium, and here the medium is the rope. So here the medium is the rope, and here the medium is the ocean. And mediums are quite important to understand when we're talking about electromagnetic radiation and maybe sound wave a little bit later. And we'll see in that respect, why is electromagnetic radiation so special? But before we do, let's talk a little bit about transverse and longitudinal waves. When we're talking about transverse waves, the idea is that the oscillation occur perpendicularly to the direction of propagation. And this is going to make sense when I show you that rope again. So if I have that rope and it has a disturbance that is propagating through it, and I can always, I can now call it as a disturbance because this is really what it is. So let's start using the terminology. And this disturbance is propagating. You can see that the amplitude of the disturbance is perpendicular. That means that the disturbance itself is in an up and down motion, whereas the direction is forward. So if the direction of the oscillation is perpendicular, just like so, this is a transverse wave. So basically any wave that assumes a motion in which the oscillation itself is occurring perpendicular. So this would be a transverse wave. And if we want, because we need example for a transverse wave, we can think of light. Light is a transverse wave. And we're going to talk a little bit about that later. And you may be wondering, what other types of waves are there? This is the only wave that I intuitively know. So I'm going to try and give you some other intuition. If I have a spring, I'm going to use a purple, no, let's use this one. If I have a spring here, let's just say I have a spring, and this is my spring, and I compress one side of the spring, let's say I compress this side of the spring, how is it going to look? And this little line here just represents a wall that it's tied to. So I just compress this side. So how would I expect it to look? I'd expect it to look rather compressed on this side, and then it's just going to be just going to be loose. And I can expect as soon as I let go of my hands here, this compression is just going to jiggle all across this spring. And what I'm going to observe, I'm just going to make it a little bit smaller. What I'm going to observe is something like this. Something like this. I'm going to observe this little spring just transferring the energy forward as if it's going to try and bounce. I'm going to see the compressed part of the spring just moving forward. So if I'm really looking at it, this is my disturbance and it's moving forward. This is my disturbance again, slightly moving forward, and it's moving across. So you can think of the displacement or the oscillation of this wave as occurring in the same direction. Why? Because I have some sort of compression here. So you can think of it as if this is my medium, the spring, and I compress it slightly more here, then I have oscillations in the same direction as the movement, because the movement is occurring in this direction. Now if I try and break it down again, let's just say I'm going to switch colors arbitrarily, and the direction of the propagation in this way. Very good. And in what way is the spring compressed? It's compressed this way as well. This is how it's compressed. If I need to compress it, I'm just going to press on this side and this side. And whereas here, if I wanted to cause this disturbance, I had to flip it up and down, which is perpendicular. So longitudinal, I would say the oscillation is in the same direction as the propagation. Hopefully it makes a little bit of sense. And if we need some sort of example, I would say sound waves, for the most part, we're going to talk about sound waves later in the course, but for the most part, sound waves show us a longitudinal wave. So once we know a little bit about those, let's keep it going, and we're going to talk about the very fundamental property of waves, and that is constructive and destructive interference. And what do I mean by that? Let's just say I toss a rock in a pond. I know I'm going to have ripples around it. Very good. Now let's just assume that right here, I toss another rock. I'm going to have some more ripples around it. I'm going to have some more ripples here. And at this point, I can imagine that this little ripple here and this little ripple here are going to, you can say meet, or they're going to meet head on. And I will actually intuitively, based on my everyday experiences, expect them to kind of cancel out. They're just going to kind of cancel out. And this canceling out is called destructive interference. And you can think of it as the magnitude of this wave and the magnitude of this wave are not going to result in a bigger wave. They're going to result in maybe a smaller, or maybe no wave. They can just cancel out. So what other way are there for waves to interact? Well, if I draw the little beach here, this is a beach and I'm in Costa Rica having fun, and I'm looking at the waves in the ocean, and I see a wave coming this way. There's a wave coming this way, and there's another wave coming this way, and maybe they would meet in a certain way that would create a larger, bigger wave here that is going to move towards the beach. And you can actually see these things happen, and this is constructive interference. And you can think of it, they adding up. And when they add up, you're talking about constructive interference. Constructive. And if you want to think about it in the physical sense, you have magnitude of wave 1 right here and magnitude of wave 2, and they result in a considerably bigger wave. And this wave is called the resultant wave. And I'm just going to put it here, resultant wave, which is just a fancy way of saying the result of these two waves. And here the resultant wave, even though maybe the intensity or the magnitude of the resultant wave is going to be 0. Maybe they cancel out entirely, but maybe they only slightly cancel out. So we're going to have a small resultant wave. And this is constructive and destructive interference. And from everyday lives, we know this is the property of waves. It's quite important to understand, property of waves. So everything that I would observe showing me constructive and destructive interference, I can say it is a wave because it acts like a wave. And what I really want to do now is just introduce you to this drawing or this depiction that you will see a lot in your course, quite a lot. And just keeping it very, very simple. This is you can say this is the frequency and the wavelength. This measurement right here is the frequency and the wavelength of the electromagnetic spectrum. And the electromagnetic spectrum is basically light. Although when we say light, we mean light that we see. But I can actually tell you that X-rays, gamma rays, we're going to talk about those, UV rays, infrared, they're all light. They're all part of the electromagnetic spectrum. But the light that we see is only in a very small range here, a very small range. And depends who you ask, and maybe the book, the minimals. Sometimes you'll see somewhere around 350 to 400 nanometers. And this is the bluer, more purplish region. And the redder region is around 700 nanometers. And you would need to know these numbers, but don't worry about it. We'll be dealing with those quite a lot. And what you need to understand is that the more you go towards the bluer range, you would have higher frequencies. You would have higher frequencies. And not only would you have higher frequencies, you would have higher energies. So this is the high energy, or high frequency range. High frequency. And we're talking about gamma rays, X-rays, and as we go to the right side, we have lower frequencies and lower energies. So radio waves of different sorts are considerably at lower energy stance than these high energy X-rays. And we know that because we have radio waves all around us, but we don't hopefully have X-rays all around us in everyday lives. The one last thing that I'd like to mention is that wavelength, denoted by lambda, is inversely proportional to the frequency. So when the frequency is, oh my God, is that enough? No. When the frequency is very high, like here, the wavelength is going to be very small. That's what we need to understand. And it's quite something that you just need to get inside your head. When you have a very high frequency, let's say light, like X-ray, it would be associated with a very long wavelength. That's really what we are talking about. A very short wavelength. Did I say long? No, very short wavelength. So when we have high frequency, we have a short wavelength. When we have low frequency, like these radio waves, they have low frequency. They're going to have a very long wavelength. Very good. So this is really what we're talking about. And if you understand that, even if you look at this visible spectrum range, and you see the blue colors, which you know they're very energetic, they have short wavelengths, and the red colors that are less energetic have long wavelengths. So if you put this little thing, frequency goes up, wavelength goes down in your mind, then you'll probably be okay, even if you get mixed up every now and then like I just did. So what I really want to do is I want to talk about the components of the electromagnetic spectrum. And when I say electromagnetic spectrum, you can just say light. Yes, light. So I'm going to talk a little bit about the components. And because we say electromagnetic spectrum or EM spectrum, it means that it does have both electric and magnetic properties. And I already mentioned that it's a transverse wave. So I'm going to draw a transverse wave here. This is my transverse wave. This is my transverse electromagnetic wave. And we already know that the direction of oscillation is perpendicular, 90 degrees, perpendicular to the direction of propagation. So the oscillation is at 90 degrees to the direction of propagation. Nice. So if I told you this yellow line here, this yellow wave represents the electric component of the electromagnetic radiation, you may ask me, hey, wait a second, where does the magnetic part of the radiation fit in? What I will tell you is I can draw another wave here, just like so, that is actually perpendicular. This line is actually perpendicular to this wave right here, which means that its direction is going to be kind of sideways, you can imagine, along this axis. So it's going to go over there. And in that sense, you would have essentially two components to this disturbance. You would have a magnetic component, and let's say my green here is magnetic. This is my magnetic component, and this is the electric component. And they are actually at 90 degrees to one another. It's kind of hard to draw, but they're at 90 degrees to one another, just like so. 90 degrees. Very good. And if this doesn't sit in your mind very well, and you're kind of struggling with understand the three-dimensional form, don't worry about it. It's not very important. All you need to know is light or electromagnetic radiation has two components to it, electric and magnetic. And if you understand that, you're good. What I really want to do now is I want to review a minimal requirement question taken from the minimal requirement question article, the Department of Biophysics and Cell Biology at the University of Debrecen. And you should really get used to using these minimals because they are really good for explaining the material, but some of them are kind of difficult to understand, or they could be. So what I want to do is I want to review this. But before I read this out, I want to pull your attention to this side. What I'm going to do is I'm going to draw a wave. This is my wave here. Very good. And what I do, I can add a wave to it because I know that waves can interact. So I'm going to superimpose a wave on top of this one in a way that the same waves are going to be in phase. They're going to be in the exact same phase. You can say that they're going to complement each other. And if I add this wave, and they're in the same phase, and we'll see what out of phase means as well, but if they're in the same phase, I can expect them to add up or to have a constructive interference. And if I have to draw a resultant wave, it would be of bigger amplitude, you can say. And you should. It's going to be a bigger amplitude wave. This is my resultant wave. The green is my resultant wave. And this is pink. This is constructive interference. And the best constructive interference is going to be when they're precisely in phase, when the peak of the blue one is on the peak of the red one, and when the trough of the blue one is at the trough of the red one. And this should be intuitive to you. You can add them up. If they're going to be slightly to the side, maybe they're going to add up also, but they're not going to optimally add up like this. And if I want them to cancel each other out, and optimally cancel each other out, I'm just going to draw another scenario here. If I want them to cancel out ideally, what I would have them do is I have this peak meet this trough. So really it would seem something like this, right around this. There we go. And you can see that they're actually out of phase now. They're counterbalancing one another. They will cancel out. Because instead of adding up the peak and the peak, I'm taking the trough and I'm kind of canceling it with the peak. So my resultant wave may be something like this. It may look like something, it may look like so. So my resultant wave is going to be smaller, and I'm going to have destructive interference, Let's see what they're trying to say here. And they're trying to say that the maximum this constructive interference takes place if the path difference between the wave is an integer multiple of the wavelength. And they will also say that the maximally destructive interference is if it's integer plus half multiplication of the wavelength. I'm going to make it a little bit more simple now. What I mean is, or rather what they mean is, that if I have a wave here, this is my wave, very good, and this is the other wave. What I want to do, if I want to have them maximally constructively interfere or add up the best way I can, I'm going to take this period, and this is my period, right? Let's say this is period number 1, and this is period number 2, and you can say that this is also period number 1 and period number 2. You say, I will take this wave, and in any form that I put it on this wave, when I have an integer multiplication of the wavelength, meaning I can start it from here. Let's just say I'm taking this integer wavelength. I'm going to start it from here. So I'm going to put it here, and this will be okay. Actually, what I can do is I can start it from this point, because this is also an integer multiplication. This would also be constructive. And if I take this one, this would also be constructive. But what they mean also is that I can take half. I can take half right here. This would be half. So this is half. And if I started from the half point, going down, I would have maximally destructive interference. And this is the idea by having either one integer multiplication or only using half of the integer multiplication. It depends where you're starting the wave from, so to speak. Hopefully this made a little bit of sense, and see you in the next video.